Dr. K. Paranivelu, Professor at the Center for Environmental Studies and Director of Center for Climate Change and Disaster Management, Anna University, Chennai. He obtained his PhD degree from Indian Institute of Technology, Madras, Chennai. He worked as project officer for a brief period at IIT Madras and moved on to the Center for Environmental Studies, Anna University in 1992. He was a visiting professor at Chungam National University, South Korea during 2007. He has been teaching courses on environmental chemistry, environmental pollution control, and instrumental methods of analysis since last 27 years. He has guided 75 students for ME and MSc, 4 MPhil, 2 MS, and 15 PhDs. He has published 135 papers in journals and 90 in conference and symposiums. He has received several awards in national and international levels.
Welcome to the lecture series on environmental chemistry. We are discussing about the chemistry of aquatic system, and in the previous class we discussed the process which actually helps in the mobility of various chemical compounds into the system, and ultimately what happens to these chemical species in the aquatic environment. So, this cover actually, if you look at the mobility of including gases, colloidal particles, organic matter, inorganic chemicals including metal ions in water is all these things are important. And earlier we have seen the processes, namely solubility, that is leaching, redox reactions, complex formation, how they help the mobility of the metals ion in this. And now we are going to discuss about the other processes, namely volatilization, sorption, ion exchange, hydrophobic interaction, settling, hydrolysis and photolysis, including the hydrolysis and photolysis process. Okay. So, in general all these processes are affected by the properties of the solute actually present in the solution and the functional group associated with the particular chemical substances. Some things are solubility of the particular compound, okay. Hydrophobicity, polarity, density, volatility, and energy content of various chemical or pollutants actually introduced to the system determine the processes, namely volatilization, etc. We will see or discuss some of these aspects now. Already we discussed about solubility of chemical substances in water, and we discussed elaborately the solubility of oxygen and carbon dioxide in natural water, and both are soluble. Oxygen is also soluble. For a healthy aquatic environment, we discussed at least minimum of 4 milligram per liter of dissolved oxygen is enough. Similarly, carbon dioxide solubility in water acts as one of the natural buffer in aquatic system. So, these species are important, already we discussed. And generally in the chemical substances, if they are polar in nature, they are more soluble in water. If the polarity is low, then usually the solubility is less. So, organic compound, when it is dumped into the environment, depending on the physical and chemical properties of the compound, it will move into the system or move out to the water system. For example, a spill of methane, if is happening, will not cause a water pollution problem, okay, because methane is a highly volatile compound. Immediately it escapes from the aquatic system. So, no issue at all with this, no pollution problem if there is a methane somehow introduced in the water system. But consider a major release of the pesticide compounds like DDT, okay, because even though the solubility is very low in water, it could cause a big problem for biota, because DDT even at very ultra trace concentration is capable of causing problem or toxic effect to the biota. So, we have to see the nature of the particular compound. So, methane being highly volatile, escape, there is no issue at all, but the pesticide like a DDT is introduced in the aquatic system, somehow it is a worry, it is considered as a problem. For this, not only the solubility, the other part of components and their property of this chemical species also important. Okay. And in fact, the water system is in intimate contact with the atmospheric air, and also the bottom of the aquatic system is intimately contacted to the soil. Okay. So, which part is important accordingly, the particular property of the particular chemical is very much. Suppose we consider water and air alone, the property to be considered are vapor pressure and water solubility. This is what is a main issue, because the previous example I had shown you, methane, you consider for methane, if a methane is introduced to the water, vapor pressure is high, immediately it escape, and water solubility in of methane is also very low. So, practically no issue at all. So, if we consider any system, air and water, vapor pressure and water solubility is a factor to be considered. On the other hand, water and soil, if we consider, adsorption and water solubility is a main property to be considered in the soil and water, because some of the components present in water may get adsorbed onto the soil component. And for this to happen, if the compound is low water soluble, definitely this will be favored, and if the compound is more water soluble, definitely adsorption of the particular compound will be very low. And suppose we consider soil directly with the air, and adsorption and vapor pressure of the particular component is to be considered. And if we consider all phases of air, water and soil with the biota, solubility in fat, hydrophobicity of the compound or liophilicity of the compound to be considered, suppose if it is in considered with the biota, all this thing. So, the pairwise distribution and the chemical property of the particular chemical species to be paid attention, what system you are going to consider, like air water or water soil, accordingly the property of the particular solute has to be paid attention. First, we will discuss about volatilization of chemical compound. So, this is nothing but disappearance of a particular chemical from water into atmosphere. Okay. This is called normally volatilization. This is actually a physical loss, no degradation is happening here. Simply the particular compound present in water escape into the atmosphere. This is normally known as volatilization. And other property as vapor pressure, and actually this is essentially the solubility of compound in vapor in atmosphere or air. And permanent gases such as methane have high vapor pressure, and they will escape into the atmosphere very easily. And as we discussed before in the previous lecture, Henry's law is very useful in this explaining the volatilization of particular compound. This is actually the ratio of a compound, that is a water solubility to its partial pressure above that water sample. This is a Henry's law, already we discussed, and this is very useful in explaining about the presence of a particular compound in water or into the atmosphere. In addition, the popular Clausius-Clapeyron equation also very handy in explaining, that is, it correlates with the temperature of gases, this particular volatilization aspect. This equation is given here, and the equation deals with two concentration at two different temperature. Okay. And usually the solubility of gases decreases with increasing temperature, and this can be found out easily using the popular Clausius-Clapeyron equation by determining the concentration of a particular compound at two different temperature, where in this equation the C1 and C2 denote the gas concentration in water of the particular compound at absolute temperature of T1 and T2, two different temperature, and delta H in the equation is nothing but heat of the solution. and R is a universal gas constant, and usually the value of R is given in 1.987 calories per degree per mole. Okay. So, that means the delta H units also N to be expressed calories in mole, not in joules. So, accordingly the values, if it is in joules, it will differ. So, this equation, Clausius-Clapeyron equation, you can find out if you know what is the delta H of the particular chemical compound, and if you measure the concentration at two different temperature, the concentration you can find this delta H, or if you know, if you do not know this, by measuring two different temperature of the particular compound, you can find out what is a delta H of the things also possible. Usually the solubility of gases in water is decreasing with increasing temperature. The process volatilization, actually there are two steps involved, that is the diffusion of the particular solute to the air water interface from within the water mass. This is the first step in volatilization. The second step is the movement of the substance away from the air water interface. Suppose you consider a particular solute which is volatile in nature is present in the water, and to escape or to lose, it has to come to the air water interface, that is normally taking place through diffusion process called diffusion. From the bulk of this water, it has to come to the top of the water, or in fact air water interface. This is happening through diffusion. So, the next step is movement of the substance. The moment it is in the top of the water body, movement of the substance away from the air water interface into the atmosphere. So, this is a second step, and this is actually determined by the wind speed, all these things. So, it is a volatilization is a two step process, and small molar mass of a particular compound and non-polar structure usually favor volatilization. If you consider a compound, the molecular weight of the compound is very low, like methane, and it is non-polar, it is highly favorable for volatilization, any solute. So, most of the hydrocarbons will easily escape, and if you consider methane and pentane, methane will lose from the water system easily, whereas pentane very low because of the high molar mass. And this can be, again the process of volatilization can be explained with the help of first order kinetic equation, and external evaporation is under kinetically controlled and not thermodynamically controlled. So, first order equation can be used to explain the process of volatilization, which is consisting of diffusion of the solute into the air water interface and then movement away from the interface. Next process explain about the movement of the solute in aquatic system is partitioning, and the Nernst partition coefficient are very handy in explaining this. The partition coefficient are the ratio of concentration of organic compound in two phases that are in equilibrium with each other. One is in water, the other one is a organic solvent. Usually we will consider as a solvent, organic solvent, water insoluble. So, this should be another thing which is insoluble in water, and such case the solute may distribute between this water or move from water into the organic solvent. And a high value of partition coefficient value suggests that the compound is not very water soluble, but is more soluble in organic solvent. So, in this case the compound is said to be lyophilic, that is more fat soluble. Solubility in water is very low. So, the K value, partition coefficient value will be very high. The solute, the K value is high, the solute will tend to be in organic, that is it is more fat soluble, that is more bioaccumulative or bioconcentrable in nature. To simulate this, the partitioning coefficient, especially in the field of environmental studies as well as pharmacology study, a model compound of organic thing, that the organic solvent here mentioned is usually N-octanol is selected as a model compound for carrying out this type of determining the partition coefficient value. So, the partition coefficient that best describe the lyophilicity is the octanol water distribution coefficient or the partitioning coefficient, and usually the symbol given is KOW. K is a partition coefficient, the O represents octanol and W water. So, this mixture of water and octanol, how much the compounds get distributed between these two is very much. The reason for selecting octanol as a solvent for this, especially in connected with the bioconcentration, is because it resembles more or less our body protoplasm. That is why the N-octanol is selected as a model compound for carrying out these experiments. So, the interesting value of KOW of most of the environmentally relevant compounds, including pesticide, range in the range from 10 power 2 to 10 power 7, okay, very high value, and it is convenient to use the common logarithmic of KOW value, because the values are very very high, very difficult to understand. So, if you take it the logarithmic value, then it will be very easy. So, KOW value is related to water solubility, and high water solubility implies a low K value, whereas a very high KOW value indicates it is less water soluble and amenable for bioconcentration, and the toxicity related to that is going to be very very high. So, the KOW of different compounds in water is very very important to understand the toxicity, including bioconcentration. The partitioning also normally as managed with fish conducting fish partitioning also, but in the KOW, the empirical equation between the KOW and the log concentration of water and saturated one is given by this equation. The saturated term C in the saturated one is also expressed in moles per liter. And suppose we carry out the experiment of the partitioning between fish and water in aquatic system, okay, to realize the actual situation or bioconcentration. The Kb value is given by the concentration of the particular solute in water to fish, including the methyl mercury, what we have discussed about Mann-Marmot disease also is applicable here. The equation is given, and if you exponenting on both the side this equation, you will get the fish partitioning coefficient value as 0.048 times of the KOW value. So, we need not conduct, few studies have been well established now. So, this empirical equation is modified further, and even the fish partitioning coefficient value can be established from this equation, that is the fish partitioning coefficient value is equivalent to 0.048 into KOW, that is octanol water partitioning compound. Most of the environmentally sensitive compounds, this value including type of pesticide is available in literature. Other important process through which the solute present in water is moved out or getting concentrated is a adsorption, sorption or adsorption. That is it is a surface phenomena. Any solid material usually have the tendency to adsorb some amount of solid on the surface. This phenomena is called sorption. So, adsorption refers to the collection of organic or other compounds, not only organic or any other compounds on the surface of particle, such as in the aquatic system, which is in contact with the soil, or suspended sediment. The sediment may be predominantly may be a metal oxide due to the insoluble nature, or from organic matter, insoluble organic matter also a component of this sediment. So, any pollutant actually present in water gets exposed to the soil and suspended sediment, which is all a mixture of metal oxides compound and organic various organic matter. So, these insoluble materials act as a kind of adsorbent agents for this different chemical solute present in the water, and most of these particles are covered with a layer of organic material. Thus, adsorption results from the attraction of two organic materials for one another, okay, like The adsorption is measured by a partition coefficient value, again not only for liquid, this is also governed by the partition coefficient value, which is the ratio of concentration of the compound on the solid to the concentration in the water surrounding the particular solid in the aquatic system. And in these, actually both physical and chemical adsorptions are possible of trace substances, including heavy metal, trace organic, everything may be binded on this material, sediment material, through a process called physical or chemical adsorption is possible. Physical, simply on the surface, whereas chemical, there is a chemical bonding is possible. For example, metal oxide containing iron or manganese is present, there is a bonding likely to be formed with this metal oxide, and chemical adsorption is possible. Suppose alumina is present on the surface, the clay soil, and more aluminum is present, fluoride is present in the water, that may be binded to the aluminum fluoride. So, like this, both physical adsorption and chemical adsorption is possible. The difference between physical and chemical is physical bonding is less, whereas in the chemical bonding very strong, chemical bonding, whereas in the physical weak forces of attraction like van der Waals forces helps this and retain the impurities on the surface of the material. And the physical other thing is easily, if it is by a physical, easily reversing the reaction or dissolving the one very easy, whereas chemical it is difficult. As mentioned before, the adsorption is again can be explained based on partition coefficient value, the particular solute concentration in water and solid, that is a sediment. If you consider any aquatic fresh system, we have to consider the sediment associated or the soil associated with the water in which it is contact. So, the concentration on the solid has units usually expressed in moles per kilogram, and the concentration in the water normally we express it in moles per liter. So, the partitioning coefficient value is actually in the unit of liter per kg. Assuming the solid density of 1 kilogram per liter, these units normally we can ignore, and the Kd value distribution will often depend on how much the total mass of the particle as organic matter, that is the sediment organic fraction, what is the thing. So, if you know this, that also can be equated by this. The Kd can be correlated by the fraction of organic material in the particles actually associated in the organic matter value. Suppose you know, then the Kd value divided by fraction of organic matter value, if you know, then we can express the partitioning coefficient value in the organic matter without doing any experiment, simply we can correlate by this. So, this process similar to the partitioning coefficient of solid to liquid or into the protoplasm in the aquatic real system, this is adsorption is another one which also can be explained based on adsorption behavior. Some of the trace metals may be bound to the material actually present in the sediment. For example, hydrated oxides of iron and manganese, especially precipitated fresh one, normally they will be present, the surface area will be very high, and for this iron and manganese compounds associated with the sediment, trace metal will be associated through adsorption process. So, this is one of the very important thing. Even fractionation or chemical speciation, what is the fraction associated with this also can be find out experimentally by suitable leaching agents. And in addition to the trace metal, organic compounds like a herbicide adsorbed on sediments and suspended organic matter like a clay and organic humic materials, and these adsorption also affects the mobility of this organic compounds, and adsorption of organic compounds is usually inversely proportional to their water solubility, as I mentioned before, and more water insoluble compound tend to be taken by strongly by the lyophilic, that is the fat loving or hydrophobic solid material, usually in this instance humus material associated with the sediment. So, absorption of organic compounds, toxic herbicide, pesticide is actually depends on what is the fraction of organic matter associated with the sediment, and that helps. Not only this, the other thing is the compound solubility in water. If you know the compound is least soluble, definitely that will be associated with the organic matter. You just consider sodium chloride and benzene. Obviously, sodium chloride is more water soluble, and that will not be associated with water only, it will not move into the organic matter or sediment part. Whereas benzene, somehow if it is introduced, the solubility of benzene in water is very, very low, and if there is a aquatic system, there is a sediment formation with a lot of organic matter, immediately the benzene will move into there, it will not be present in the water. That is what the solubility of the particular organic solute in water is determining. If it is more water soluble, adsorption is poor. If it is less water soluble, the adsorption will be very high. So, that is a problem actually associated with the sediment particle. Also, that is pore water consisting of water held by sediment inside this solid mass, okay, that is actually present inside the pore, is also an important reservoir for gases in natural water system, which determine the absorptive power of this one. In addition to adsorption, sometimes ion exchange reactions also possible with especially the bottom sediment. The bottom sediment, where condition is anaerobic and rich in organic matter, is different from wet soil, that is aerobic and low in organic matter. So, if we consider these two cases of sediment at the top and the bottom, they are entirely different. The wet soil actually is aerobic and low in organic matter, and whereas the bottom sediment is anaerobic and high in organic matter is actually a different thing. The bottom sediment having a cation exchange capacity value ranges from 20 to 30 milli equivalents per 100 gram of the sediment. The bottom sediment have this one. So, they have appreciable amount of cation exchange capacity. So, that means they can exchange any cations are present in aquatic system, there is a possibility there is a exchange with this bottom sediments as well as soil. And sediments are again important repository of metal ions that may be exchanged with the surrounding water. If some toxic metal ions are present in water, there is a possibility they may be exchanged with this one. Because of their capacity to absorb and release hydrogen ions, sediments have an important buffering capacity in water. The H plus ion released all these things associated with the sediments, and they act as a kind of a buffer. Not only this, ion exchange reaction in buffering the water system is also very, very important. So, to some of the other processes actually determining the mobility of both organic and inorganic components, volatilization is the one in which organic compounds which are very easily volatile will escape from water system into atmosphere. If it is organic compound, they will undergo further photo degradation as we discussed in the atmospheric chemistry. Ultimately, they will be converted into carbon dioxide. So, apart from this volatilization, we have other processes, namely partitioning of particular solute into the liquid organic solvent is possible, or organic matter, and also adsorption on the surface of the organic matter, that is a sediment part in which both organic matter as well as metallic oxides and hydroxide may be a component. There also the metal mobility and organic things are associated with this. And finally, ion exchange reactions also possible in determining the mobility. Some of the toxic metal actually released into the environment or the water system may have a chance and interact with the bottom sediments which have considerable cation exchange capacity value, that also possible. And in place of this adsorbed metal ion, H plus ions may be released into the aquatic system, that will actually taking care of the buffering capacity of the system and helps in the mobility as well as maintaining the pH value of the system. So, with this we have seen the most of the organic compounds and inorganic components, how they get exchanged or moved into the system or out of the system. With this, we complete the part. Remaining thing we will continue in the next class. Thank you.